Alright, so we're ready to start talking about now analyzing transformers in the frequency domain. We talked about transformers a tiny bit in the previous course, but we really didn't get too far with them because the way we looked at them, we ended up with a system of differential equations, which, yes, you can solve using matrices and eigenvalues and things of that nature, but we just set the equations up. What we're going to do here is we're going to look at transformers, and again, we're not going to be concerned about the transient response. We're just going to look for the steady state. So let's just remind ourselves a few things here about a transformer. A transformer is represented by basically two inductors that are close together like this, and then we have, our dot convention here. And then, of course, we have other circuitry going on here. Now, remember, we had several voltages here and currents. So we had a current in the primary coil. Remember, we called this the primary coil. And we had a current I1 that we would draw. And then we had a current I2 in what we called the secondary coil. Now, I'm going to go ahead and just add in some additional components just so that we have a completed circuit. We're not going to actually analyze this problem, but we want to just talk about how we would analyze it. So I'm just going to put a resistor here, and then I'm going to put, I'll call this R1, and then this RS, and then a voltage source here. So if you remember, what we wanted to do was write loops here. But remember, when we wrote these loops, we had to be careful of something called the dot convention. So remember, we had something called the dot convention. And I should put up here L1, L2. And the dot convention was that if the arrow goes into the dotted side of the coil, the induced voltage has a plus sign on the dot. And then the exact opposite was the case if the arrow goes into non-dotted side of the coil. The induced voltage has a plus sign on the non-dotted side. So hopefully this is familiar. We talked about this dot convention in the previous course, and we also talked about the mutual induced voltage here. And one thing we should add to this diagram here, I'm going to just move this a tiny bit here. We should also add in here, remember that we had, when we had these two inductors coupled together, there was this mutual inductance here. And so if we kind of look at the way this one is set up, I'm going to go ahead and draw all the voltages if we were to do this loop here. So let's look at this left-hand side one. So if I were to do this loop here, I'm going to have voltage across the resistor here, plus minus, and then we're going to have plus minus a voltage across the inductor due to the current I1, but then the current is entering the dot, so that creates an induced voltage, and since it's entering the dot, the plus sign is on the dot here, and this would be VM1 is what we usually did as far as our convention, because it's due to the mutual inductance, but it's due to current 1. But this is in the secondary coil, this voltage. This is not in the primary coil. All right, and then you kind of do a similar thing for I2 here. Well, we would have a voltage across R1 plus minus, and then given the direction of the arrow, we'd have a plus minus VL2, and then I'm going into the non-dotted side of the coil. So since I'm going into the non-dotted side of the coil, that means my plus is on the non-dotted side of the coil, and then I have a minus, and this would be VM2. And so if we were to write these loops here, and let me just label this voltage source VS, if we were just to write these loops here, we're not going to write any equations down, we're just going to write the loops here. So loop 1, we'd have minus VS plus the voltage across that source resistor plus the voltage across the inductor, VL1, but then we also have this induced voltage, VM2, but the arrow's hitting the minus side, so it would be minus VM2 equals 0. And then if we did the loop 2, we would have, well, I'll just start with the resistor, VR1 plus, and then we'd have this VL2, and then again the current's hitting the minus sign of my induced voltage, so it'd be minus VM1 equals 0. So these would be my two equations that I'd have. And what we're going to do now, when we get into the analysis and in examples here, what we're going to be able to do is actually just go ahead and use these loops here, and then just put these in phasor notation, use the impedance like j omega L, and then that impedance times current is voltage to get, we'll still have a system of equations, but they'll just be algebra equations with complex numbers, so they'll be really easy to solve for us. So there's something else we need to make sure to discuss though before we go to an example problem. And remember, there's something here that we had M is what we called my mutual inductance. And recall that M was equal to K times the square root of L1 times L2, where K was called the coefficient of coupling. All right, and the coefficient of coupling is unitless, and the coefficient of coupling, I mean, technically it could be 0, so I'll go ahead and do that. But if it's 0, that means the inductors aren't coupled at all, which means you don't have a transformer. That means the inductors are isolated from each other, shielded from each other. So while technically you can have one, it's kind of a nonsense case. But the maximum value for the coupling coefficient would be 1. You can't get that. And 1 actually is an ideal circumstance. In practice, you can you technically will never get 1. You might get like 0.9 or something, but actually obtaining the coefficient of coupling being 1 is not actually realistic. All right, so before we do some examples here, let's talk about the other type of analysis we looked at here, where we had ideal transformers. And remember here, what we had is we had some assumptions. We basically said K was equal to 1, and L1 equaled L2, and they were infinite. So we had infinite inductance, and that means our mutual inductance is infinite, basically meaning that we are completely coupled together. And when we made these assumptions, we came up with some much more simplified equations here. And remember that there was like, quote, 4 cases that you could do here. But what I really like to do is just draw the one and just always put my problem into this situation. And so we would have this here, and then remember we usually had 2 vertical bars. That was kind of indicating that it was an ideal transformer. And we still had our dots for our dot convention because that was still important to have. And then what we had here is you want the current on the primary side to be going into the dot, and then you want the current on the secondary side to be leaving the dot. And then what we ended up having is we'd have this plus minus V1 on the primary side and plus minus V2 on the secondary side. And then we didn't have a coefficient of coupling, but we had N1 to N2. And remember, N1 to N2, whoops, come on, there we go. N1, I didn't get that right. N1 to N2 was something we called the turn ratio. And with this ideal assumption, we actually got some very nice equations here. What we had was that V1 over N1 was equal to V2 over N2. And then we also got that N1 I1 was equal to N2 I2. So we had some very nice relationships, and because of this, this really already gives us two equations. Yeah, there's four unknowns here, but it gives us two equations already, and so you can just write two more equations using loops, and you'd have four equations, four unknowns. What we typically would do, if you remember, is that we would use these here to substitute in and simplify equations. So that's again doing this N1 to N2. And remember, when we said the turn ratio, it was literally referring to like the number of turns of the coil, like the wrappings compared to the other one. And we also noticed that if the voltage on the secondary side, I'll write this down here, if V1 was less than V2, in other words, that the voltage stepped up here, we had then that I1 was greater than I2. Because you could step the voltage up, but you would lose current. Or if V1 was greater than V2, so you're stepping the voltage down, you would wind up having that I2 was greater than I1. And if you think about it just for a second, that does make sense. If we're assuming ideal cases, and power should be conserved, so power in the primary loop should equal power in the secondary loop. Now we should think about this. This is never true in reality, because there's always going to be losses of heat, and if you've ever been around a power supply, like even your computer's power supply, it always puts off heat, and that's because this transformer isn't ideal, and there are other components, of course, that are heating up and making heat for your from your computer, but these transformers will actually heat up, so the power is never conserved, and some of that power is being lost in heat. Alright, so we're going to wrap this video up here, and then the next couple of videos we're going to do some example problems. We'll do one just with the non-ideal transformer, and then we'll do one with the ideal transformer.